This is Smarter Cars, a podcast about autonomous vehicles.
This is the finish line. The Stanford racing team has made its way into the history books.
But the most important thing for me is it actually doesn't matter who comes first. It matters that we as a community achieve it.
Early in a technology, 1,000 flowers should bloom.
Welcome back to Season 2 of Smarter Cars. This is your host, Michelle Kairouz. Today we're talking with Sam Anthony, the CTO and co-founder of Perceptive Automata, a company making software that helps autonomous vehicles understand human behavior. Sam, welcome to the show.
Happy to be here.
Great. Can you start by telling us what Perceptive Automata does and what problem you're trying to solve?
Sure. So Perceptive Automata is building a module for self-driving cars and for advanced driver assist systems that helps vehicles understand people out in the world. So a pedestrian, are they waiting to cross the street or are they waiting for a bus? A cyclist, do they expect you to yield to them? Another car, you're making an unprotected left turn, are they going to let you go or are they oblivious? So we build a module that gives self-driving vehicles and advanced driver assist those kinds of insights, and it gives them those kinds of insights in the way that a human would make those judgments. So a guess about what's in the person's head that's as behaviorally relevant as what we do as people.
It seems like you're trying to help autonomous vehicles understand humans and their intentions. Why is this such a hard problem for autonomous vehicles? You know,
traditionally, the way that roboticists think about the world, the way that computer vision thinks about the world, is there's ground truth out there, and what you're trying to do is recover the ground truth. So, you know, this thing in front of me is a tree. This thing in front of me is a person. This person is moving at half a meter per time interval. If you frame the world that way, the question that we're answering seems impossible, because what we are trying to get at is locked away in people's heads, right? Like, does somebody want to cross the road? Well, only they know that. But right? I mean, right. It's unless you have a telepathy ray, and I don't think we may have a competitor with a telepathy ray, but I haven't heard about it. So. But as humans, we can do this, right? So when we're driving down the street, if we see someone, even though, you know, we can't know for sure that they're waiting to cross the road, well, they want us to know. It's behaviorally relevant information. We know how to kind of make an estimate of that that's the right estimate to pilot the vehicle. In order to build that into an automated system, what you need is a really deep ability to understand and model how humans look at the world. So you can't do this using the standard techniques of computer vision or of robotics, where you draw a box around the person and then figure out which way that box is going and then make inferences from there. You really need to be able to look at how someone is presenting themselves, their appearance, these very subtle nonlinear cues, like whether they have tension in their shoulders, whether they're clutching their bag they're carrying just a little bit tighter, whether they have a quizzical expression. So you need to be able to pick that stuff up and use that in the same way that humans do to be able to make judgments that are relevant to motion planning this kind of way.
Yeah, it's funny. People always say that things that are hard for robots are easy for humans. When the robot apocalypse happens, we should just shut the door because, robots have trouble opening doors. Is this kind of the fundamental problem here?
It exactly is. Yeah. So the reason that there's such a gap is that this is part of the human cognitive toolkit that's really kind of central. Like, it's one of the most important parts of what makes our brains different from the brains of other animals. It's something that we've, looking at another human and using these kind of social cues to understand them and understand what they're thinking about and what they want is something we've evolved to be good at it. It's core to our kind of identity as social beings. So we're so good at it, we don't even really notice we're doing it. Like when you're driving along the road, you're not saying to yourself, oh, I just looked at that person and evaluated that that person is not salient to the driving task because they don't look like they're going to cross the road for reason A, reason B, reason C. It happens. It happens transparently and effortlessly.
Right. It's interesting because I think, the industry has focused on what is problematic about humans as drivers. We get tired, distracted, impaired, angry. We have too little experience when we're young, and then we lose our vision and reflexes when we're old. And all these accidents are caused by sort of what's wrong about humans as drivers. It sounds like you're trying to figure out and mimic what's good about humans as drivers. Is that fair?
What I always say, yeah, no, it totally is. And kind of what I always say about that is, how good a driver do you have to be able to do it mostly successfully while not paying any attention? I mean, so, humans get distracted and they get angry and they do stupid things. In part, they believe that it's possible to get away with doing these stupid things because the sort of general understanding of the world and the general understanding of the task of driving that humans have is so sophisticated. Like you can tune out. You can literally not be paying any conscious attention and still mostly get where you're going. That's astounding.
It is true. I mean, how many of us, sort of drive along the freeway and suddenly find ourselves exiting and say, wow, I don't even remember getting here. Yep. So when we talk, it's interesting because when we talk about the standard for safety with autonomous vehicles, people generally say an autonomous vehicle has to be as good as a human driver, but it's usually thought of as a statistical problem, accidents per mile or something like this, which means really as good as the group of humans overall with all the defects they may have as a group, which is very different from asking if one autonomous vehicle is as good as one perfect human driver head to head, where that driver's, not suffering from these human flaws. How do you think we should think about standards for safety measuring against humans?
Yeah, I mean, so I think that's the question of what it means to be as good as a human is actually a super complicated question. And there's sort of this industry has kind of it has this great origin story going back to the 2007 Urban Grand Challenge. But if you go back to that, to the Urban Grand Challenge, the target for these vehicles, the stated aim for that Urban Grand Challenge was a vehicle that can get through this course, but really a vehicle that could pass the California driver's test. And on some level, that's kind of a nice goal. It's bounded. It's pretty clear. You can look at the California driver's test, tells you what you need to be able to do. The California driver's test was designed to be taken by humans. So there's a built-in assumption there that everyone taking the California driver's test, can look at somebody else and can say that person's sad, for instance, can empathize, can understand that little kids are different from grown-ups. So there's a lot of assumptions built into that. And I think similarly, there's a ton of assumptions built into this sort of idea of fewer crashes, right? Which is that when a human crashes a car, we think about it in a very particular way. So we think about blame. We think about what might have been going through their head that led to them making the decision or failing to notice the thing that caused this crash. With an autonomous vehicle, what does that mean, right? So if you think about when the tragic Uber crash happened, one of the things that I think shocked people was the idea that this vehicle could just straight up not recognize a bicyclist in the road, because that's something that wouldn't occur to us as humans. It's something that's so easy for humans that we wouldn't kind of get that as really the problem.
Right.
So I think when you're talking about safety, it can't just be, do they, pass the same tests as humans do? Do they at a average level cause fewer incidents than humans do? Although, believe me, there's a huge value to them causing less incidents, but it also has to be can they see the world in a way that's meaningfully complete by human standards? When they have an incident, did that incident happen for reasons, that are understandable to a human? Is it the vehicle doing something where you could say, oh, I completely understand the decision-making process, and obviously that's not the fault of the vehicle? Or is it something where you're saying, wow, that's something that a human would never, ever have done? Because I think if it's the latter case, if these vehicles are doing things that humans would never do, even if the absolute number of incidents is lower, it's going to be very, very hard to integrate them into roads and integrate them into sort of greater society.
Yeah. So if you were crafting a driving test to test autonomous vehicles, what would it look like?
I think that's a good question. So that's a hard question. I think it's a question I'm not all the way there on. The way I've been sort of thinking about it lately, and this is kind of a terrible phrase for it, so I probably shouldn't even say it on a podcast, but there's sort of the human smell test. So you take a difficult situation, you put the autonomous, maybe even a situation where there's no good outcome. You put the autonomous vehicle through it in simulation. You say to people, well, this is the information it had, and this is the decision making it made. And then the question is, when people see that, do they say, I understand that or not? Right. So it's a little bit, it's hard to kind of codify it. It's hard to make it into something that's strictly empirical without thinking about like, well, what people do you ask and how do we measure? But really that sort of clearing that bar of explainability. And again, that definition of what explainability means is going to be tough, but clearing that bar of explainability to my mind is like the first step. And then the second step is you can't crash these things. It's not just that they have to be better than humans. They have to be, starting from a target of perfect and then getting as close as they can. But then also they need to be explainable. And so I think you need this sort of, vision zero for AVs. And then you also need, when you deviate from that, to have that be something that is comprehensible, is meaningfully human enough or understandably superhuman such that people don't see it and go, what on earth happened? This is terrifying.
Yeah, that is the problem, is that there may be fewer accidents, but they're going to be different accidents than the ones that humans, would have caused. So you're suggesting we should maybe have some upvoting and downvoting, give people a thumbs up as to whether it was understandable.
And I don't want to fully crowdsource it, right? If you get whatever, you're going to have like Reddit subthreads about how you troll self-driving car companies and do it. So not that, right? And that's why it's a little bit inchoate. But I do think there's something very powerful and very necessary about the idea of it needs to be what they see and what they understand about the world and how they make decisions based on that needs to be meaningfully complete, specifically from a human perspective, and from the perspective of other drivers. And I think on some level, it's not going to be upvoting and downvoting, but it's going to come down to people knowing it when they see it, really.
Yeah. So, you mentioned the California driving test. It is interesting. It's not, when you apply to get a California driver's license, it's not just that you take a road test. You also have to pass a written test, and you also have to pass a vision test, right? You have to sit there and read the eye chart across the wall. So there are a few other steps there, and maybe there's some equivalent thinking about that for autonomous vehicles.
Well, and again, like they definitely should be able to pass the California driver's test. The written test, all of the things that are captured in the written test should be there in the planner. All of the things, the vision test, certainly the level of acuity and the level of distance vision that test should certainly be a part of the sensor set on these. But it kind of has to be more than that. Like when you do the California driver's test, no one asks you if you can tell that a tree is a tree, right? Because it's assumed. No one asks if you understand what it means when somebody waves at you, right? It's assumed. And so there are going to be additional pieces which are really answering sort of parts of the question. It's almost like little mini chunks of the Turing test, right? So when you're talking about a police officer who's indicating something to these vehicles, do they have the ability to understand that for situations X, Y, and Z? When there's a unsignalized crosswalk and there's somebody standing at the crosswalk, do they have an ability to, and this is something we would do, say, okay, well, if you ask 100 people, 98 of them say this person wants to cross the road, is the vehicle also going to make that judgment? So I think it's not that the California driver's test isn't there, it's just that the secondary question of what are the capabilities of these vehicles it has, I think, an important part to play in how we as an industry, self-regulate, or at least kind of talk about what these vehicles are, so that people who have to interact with them, people who have to think about integrating them in cities can understand what they're dealing with and can come up with frameworks to interact with and to deal with them.
So let's talk about how your software works. I think you describe the components of what you focus on as intention and awareness. Can you explain each of those and what the software is looking for to try to ascertain intention and awareness?
Yeah, so we define those pretty specifically, actually. So for us, intention means not, is this person going to step into the road, 1 second out, but does this person want to cross the road before the ego vehicle gets there? So it's really a question about what's in their head, what their goals are as it relates to the task of driving. Similarly, awareness for us doesn't mean, is this person looking at you? It means, does this person know that the vehicle is there? And the way that we get at this, or the kind of the way to think about these models at a high level, let's take intention. Imagine that you had your autonomous vehicle and you had 100 people in the vehicle with you. You saw a pedestrian. You said, okay, 100 people in the vehicle, let's take a vote. Does that person want to cross the road before I get there? Those people vote on it. That's going to give some kind of sort of distribution of results. That's really what our models are outputting. So it's the target for our models is the distribution of human responses to this question. And so that's what they're doing. That's the kind of questions that they're answering. That is in a lot of ways, and I'll get to the second part about how we train this in a second, but that is in a lot of ways a much more useful signal than asking, are they going to cross? Because when you're standing by the side of the road and you're a pedestrian, you want to cross the road. Are you going to step into the road now, or are you going to step into the road a second and a half from now? Well, that's dependent on a lot of things. It's dependent certainly on, this autonomous vehicle that's coming towards you. It's also dependent on vehicles behind them, bicycles, a vehicle that you can see around the corner, but the autonomous vehicle can't, a shiny thing that distracted you, something you just remembered about leaving the fridge open. So when you're trying to understand people, when you're trying to make decisions about how to act around people, you need to kind of get at these higher level questions of their goals and their understanding, because the lower level questions of kind of when are they going to step in the road are rapidly become impossible to answer the sort of when you're more than like a half second away from them. And
what are some of the factors then that you're looking at? Is it eye? Is it posture? Whether they're carrying a bag? Like, what are some of the factors then that you're looking at in the scene that go into that analysis?
Yeah. So the short answer is it's all of those and many things besides that we don't even necessarily have a good picture on what they are. What we do to train models we take training data, which is data from sensors from autonomous vehicles. So, for instance, for intention, we would take data from a front-facing camera from a vehicle driving around. We extract from that relevant interactions. So there's a pedestrian that the vehicle drives past that might or might not want to cross the road. We take each of those relevant interactions, slice it up into very short slices. We take those slices and then we manipulate them. And this is sort of the key step, because we will take those individual little chunks of driving data and we will make parts of them easier to see, harder to see, more salient, less salient for humans. Then we show those modified versions to lots of people, ask them kind of different kinds of questions, and end up with, for each little chunk of this driving data, hundreds of pieces of information about how people answered these questions we're asking when they were sort of forced to use different visual information. And
so is that disassociated? Is that, are you saying when you magnify different parts, are you saying that you're asking about each different little piece of the scene independently so that somebody's evaluating it without the benefit of the 6 other pieces of information in the scene?
Right. So and when we do this manipulation, by the way, we're not saying like, okay, well let's only show their left arm, let's only show their right arm. It's kind of much lower level than that. It's like, all right, well, let's blur out, everything except for one dot and see how people do. Oh, it turns out that dot is completely irrelevant. Let's try it somewhere else. So we what we get at with this eventually through a pretty laborious data collection process is a characterization for that training sample of really specifically what parts of the training sample on a pixel level are relevant and what parts are sort of, mess up people's ability to make these judgments, what parts emphasize it. And then we feed all that to a neural network. Like that's our training set that goes into a neural network. And then at the end, what the neural network cares about when it sees a new sample out in the world is whatever's there in the pixel data that maps back to what was diagnostic for people. And that can be these like weird kind of nonlinear, kind of subtle features sometimes, and sometimes they can be pretty understandable, but something we didn't predict. So, for instance, after we started training these models, one of the first things we noticed in our evaluation process is that our intention model cares a lot about bags. So if somebody is holding a bag or has a bag next to them or has a bag on their shoulder, our model cares a lot about that. And what we eventually figured out is that as humans, when you're carrying a bag, the way you're carrying it is very diagnostic over whether you think you're going to start moving soon. So somebody with a bag down by their side, they're going to pick the bag up before they go. But even somebody who has a bag on their shoulder, if they're going to start walking across the street or think they might, they tense up a little bit. They hold it a little bit differently. And so that's a feature that our models care about that we didn't predict that they would care about, right? So we didn't model bag having. We didn't ask people to rate images with bags and without bags. It came out of this training process with these manipulating images and asking large sets of people about.
So some factors were more indicative of intent than others.
Exactly. So some things in these images that, it might be obvious things, like if somebody is taking a big step, then definitely that's indicative. Our model's going to figure that out. Or it could be these very subtle things, like just a little subtle change in the way somebody's holding a bag. And what happens through our training process is that we can kind of pick up all of those things, whether they're obvious or subtle or localized to one part of the image or just something about the overall cast of the image. And then all of that kind of comes into our model, and our model at inference time pays attention to all of that stuff.
And what about certainty? Are you weighting the data differently by how certain a human would be when faced with that behavior? Like maybe sitting down on the curb and opening a bag is sort of more certain that you're not going to cross than if you're just standing on the curb talking on your phone? Are there different weights, or how does the algorithm adjust for that?
Yeah, that's a great question. So without getting too deep into stuff that's sort of part of our secret sauce, things like that come out of the training process. So things like that, this person people are unsure about, this person people are really sure about, but the answer is unsure, things like that. Basically, the way that we collect this data, that's part of the training data. So that gets in kind of automatically.
So if a human would have no idea what's going on in the scene, something really crazy is happening, do your algorithms register that uncertainty as like, hey, something's crazy is going on here, we don't know what's going on?
Yeah, well, exactly. So I'll give you an example. In practice, if you think about pedestrians, there are different classes of pedestrians, and some classes of pedestrians are extremely predictable. Other classes of pedestrians, let's say kids or people who are drunk or otherwise altered, are much less predictable. That the training for our model and then the output of our model reflects that uncertainty. So if you have a vehicle that has our software installed and you come upon someone who's, stumbling drunk, what our model is going to say is, well, here's our intention value, but also this is really ambiguous. And that's a very useful signal in and of itself, because, if someone's definitely going to cross the road, that's one thing. But if those 100 people in your car would have no idea what to say about that, that's also an extremely important signal for the motion planner in the vehicle.
Right. So it seems like your algorithms on the whole operate, to reflect the views of a collective group of humans, like a consensus view. How much like humans are your algorithms? Are you measuring kind of how good they are at mimicking what a human would think of a situation?
Yeah, so perfect performance for us is that the output of our model is indistinguishable from human judgment. So it's indistinguishable from what the consensus judgment of people would look like. And we're about 85% of the way there. So our outputs from our models are about 85% of the way similar, and in practice that metric's a little funny because you're talking about a distribution and how things fit in a distribution, so there's a little bit of statistical complexity in how we calculate that, but in general, probably the way to think about it is that 85% of the time, the outputs from our model are statistically indistinguishable from the human judgment.
And are you only evaluating other humans in the scene, or are you also looking at objects or animals?
We aren't. So we're looking. We focus on humans and human-operated vehicles, right? So pedestrians, cyclists. A little later this year, we'll have a product which works on human-driven vehicles. Animals are tricky because our target is this human ability to judge what's in the head of another human. And when it comes to an animal, we don't really. We probably will make those judgments, but like if I see a deer, I don't know what the deer wants. I don't have deer theory of mind. So in general, we think that this is really specifically going to work for humans and human-operated vehicles.
Right. So you're creating a software module. How does it fit into the larger autonomous vehicle software stack? Like, where does it sit in the stack?
Yeah, so basically we take input from the perception system. sensor data or sometimes sensor data that's had a little bit of perception work done on it, like the scene's been segmented or something like that. We take that as input, and then the output is this data structure which captures state of mind, which can then be injected at a whole bunch of points in the prediction stack or directly into motion planning, depending on how people have architected their overall stack.
So if the autonomous vehicle with its own path planning module was planning to keep driving and not stop, and your software were to have an output indicating that a pedestrian was going to cross in front, how does that get reflected in the autonomous vehicle behavior?
Yeah, so let me kind of build a more specific scenario around that, and then I can kind of talk about. So, for instance, say the autonomous vehicle is heading towards a crosswalk that's an unsignalized crosswalk, and there's a person who is standing still at that crosswalk. If you're using, if your current prediction system is an extended Kalman filter, the extended Kalman filter is going to basically say, well, that person's standing still, so the best estimate we can make is that that person's going to continue to stand still. That would argue for a motion plan where you continue going at the same speed. Then, if the person does step into the street, you have to make a really substantial emergency maneuver, and it's no fun for the people in the vehicle, it's no fun for the pedestrian. With our system, for instance, that person who's standing still might have a very high intention score. That very high intention score could be used to modulate the vehicle speed down, not stop it, but modulate the speed down, the assumption that you may not have to stop, but if you do have to stop, if you've modulated the vehicle speed down, then it will be less of an emergency stop. You won't be hitting the deceleration limit. You won't be smacking people's heads into the backs of chairs or anything like that. So that's one example. Another example would kind of go the other way. So if you have a vehicle with an automatic emergency braking system, there's somebody who's standing in the road. Under many ordinary circumstances, that vehicle was, standing close to the car's path, not necessarily in the car's path. Much of the time, those systems would activate because that's kind of within the tolerances for what they think of as the vehicle's path. It could be the case, and often is the case, that person is in the road because they're getting into or out of a car, and they're not going to proceed into the road. So in that case, we would potentially give a very low intention score, and in that case, maybe you would still modulate the vehicle speed down, but you wouldn't activate the automatic emergency braking system.
So does your software then work with both ADAS systems as well as level 4 autonomous vehicles?
Yeah, that's right. We've designed it to be able to integrate well on actually, AEB is, I think, technically level 1, so level 1 all the way up through level 5.
Okay. And what type of assisted driving features are most helped by understanding human behavior? Is it the automatic braking or? Yeah, without getting, I think that in general, and I don't want to be, some of this stuff I want to kind of, there are customer relationships that so I want to stay pretty broad, but in general, the kind of next generation of ADAS features, right now you have, lane keeping, you have highway adaptive cruise control, you have some degree of lane change. The next generation of these ADAS features is going to have a lot more functionality that involves dealing with humans, so pedestrian crossing detection or automatic emergency braking or more sophisticated lane change functionality or merging functionality for highways. That kind of next generation, when you get to more human interaction, is when our model outputs start to be really helpful. Great. Recently, there was a report about a Waymo vehicle successfully navigating through an intersection where the stoplight was out and a police officer was waving cars through. Are there cars today that can understand that type of hand signal, or do you think something else was at play there? And then is your software going to be helpful in that type of interaction?
So I would wager that the Waymo vehicle has some ability to detect hand gestures and kind of do action recognition. In the research literature, that's a problem that people have been looking at for a long time and are not too bad at. And in terms of companies that take this kind of problem very seriously and are very sophisticated about it, I certainly think Waymo absolutely checks both of those boxes. Where I think we're helpful is those kinds of interactions, that kind of interaction where a light is out and you have a police officer waving people through, it's actually relatively straightforward as far as human social interactions go. Where we would help is in situations where the behavior is still just as easily read by humans, but doesn't map so kind of tightly to a characteristic behavior. So you have a police officer working at a construction site, and a car comes by, and they're annoyed at the car, but they're not exactly telling the stockkeeper waving them through, or they decide they need to cross in front of the car and assuming the car is going to stop. So there's subtleties to this behavior that above and beyond just a cop who's really signaling traffic. And I think when you get to those subtleties, and I think in practice those subtleties form the bulk of human interactions on the road, that's when the generalization performance and the I guess subtlety of inference that you get with our kind of approach becomes the solution you need to go to.
There was also a report recently of a study that showed autonomous vehicles not recognizing humans with darker colored skin as pedestrians as often as white people. Are you familiar with that? Have you seen anything like that? How would you account for that to avoid that type of problem?
So it doesn't surprise me, frankly. Coming from the machine learning world, data set bias is an enormous problem. I think in terms of that, I have no doubt that's, I mean, I read the study and it certainly does show what it purports to show. And what it purports to show is that camera-based pedestrian detection systems do worse on non-white pedestrians. The couple things about that I would say, first of all, camera-based pedestrian detection systems don't do that great on anybody. So even for white pedestrians, I don't think that any vehicle out there now is or should be solely relying on camera-based detections for pedestrian detection. Certainly, any vehicle that has LiDAR on it, they're going to be doing sensor fusion with LiDAR and camera. That's going to massively reduce the gap because LiDAR isn't going to have these kinds of problems. And I think as the camera-based systems get better, there's definitely a lot of work to be done to narrow the gap. But in terms of the practical implications, fundamentally there's a long way to go before camera-based pedestrian detection is going to be anyone's sole or primary solution to detecting people out on the road.
Yeah. So looking broadly at the autonomous vehicle landscape, some people feel that the industry is taking longer to develop level 4 vehicles than perhaps was anticipated. From a software perspective, what do you think the holdup is in terms of getting level 4 vehicles safely deployed, say, in a ride service context?
So I think one of the things about this industry that is under-recognized is, first of all, the astounding amount of progress that's been made. Like from 2007 to now, that we've been able to get these vehicles to the level of performance they're at is just a stunning achievement. It's an engineering feat that I think has very few parallels in other commercial enterprises. Part of the reason it's so amazing is that this is a really, really, really hard problem. This is one of the, just from a perception perspective, from a behavioral planning perspective, even from a controls perspective and a compute perspective, this is an incredibly difficult series of engineering problems. I think one of the things that's happening now, there's an adage in software engineering, that the first 90% of the work takes 90% of the time, and then the last 10% of the work takes 90% of the time. So I think what's happening now is that as the people who are making and deploying these vehicles have gotten closer and closer, the problems that remain are the ones that are the really hard problems, and the ones where the approaches that are sort of the standard approaches have not borne fruit or are sort of not up to the task. For us, we feel like understanding humans is the biggest one of those. That's kind of the largest remaining challenge for these vehicles, because humans are so good at it. And so what we'd like to do is kind of, as these vehicle makers that have surmounted so many engineering challenges reach this last 10% and kind of start to face up to what an enormous problem understanding people in the world is, we can say, well, look, we have a solution that solves the hardest parts of that for you.
Right. So are you partnering with OEMs or tier ones or other companies with respect to the software module that you're offering?
Yeah, so I can't really name names, but we have commercial relationships with OEMs and tier ones and mobility startups. So we're working with people doing level 4 and 5 in constrained environments, also with tier ones doing ADAS products, also with OEMs who are kind of doing both of those things and thinking about full self-driving for production.
So is your software being used in any of the test cars on the road today?
It's implemented in test cars. It's deployed in people's autonomous stacks. I would not want people to assume that if they see a vehicle that vehicle is using our software for inference related to its motion planning right now. But that will increasingly be the case. I would say this year that it's actually deployed in these vehicles as they're driving around.
So if it's deployed in vehicles, and even if it's perhaps not directly connected into their path planning, are you able as a company to get some feedback as to how it's working?
Yeah, absolutely. I mean, and that's the real value. So the kind of selling into these companies for any vendor is an extremely lengthy process, and certainly we're no different. So what we're able to do with these partnerships is first of all, this is a customer relationship. They're certainly paying us to provide them with things, but also we're getting a much better understanding of specifically what the safety and compliance and performance criteria are for their specific use cases. Great.
And what do you see the goals for the company in the next couple of years, 2019, 2020? What is the company hoping to accomplish?
So I think really to hit the marks that we need to show the value for our customers and be well along the path to production deployments.
Great. Final question. You recently joined the PAVE Coalition, which I think stands for Partners for Automated Vehicle Education. Why did you join, and what do you see are the biggest challenges for autonomous vehicle education?
So I think we joined because we feel like we have something to say about how to build trust for these vehicles. And we were talking about this earlier in the call, when you sort of talk about the bars that these vehicles need to clear to be accepted and to be sort of comfortable for both people in them and people who interact with them from outside the vehicle. The questions of explainability and the questions of to what degree they are like and diverge from humans and how to think about those things, I think is something where we feel like we can usefully contribute to that discussion and usefully contribute to this kind of process of building trust and confidence in these vehicles.
Great. Well, thanks so much for coming on the podcast. This was a really interesting discussion. I appreciate you taking the time.
You're welcome, and thank you so much for having me.
All right, take care. Thanks again to Sam for joining us. If you're enjoying the podcast, please leave us a review or rating on Apple Podcasts, Spotify, Breaker, or wherever you listen to your podcasts. You can find the show notes for this episode and all of our episodes on our Medium publication called Smarter Cars. Thanks again for listening. We'll see you next time.